So we're going to start working on problems in section 6.4 where we're going to be solving first order systems. We have the background information now to do that. So we've said that we can write a first order system in a matrix form like this, x prime equals ax, where again we're going to work with 2 by 2 matrices. So A is a 2 by 2 matrix A, B, C, D, where those are just real numbers, or any type of number actually. X is given by this vector function where we have a function of t we'll call little x in the first component and a function we'll call little y of t in the second component. So we're ultimately finding both of these solutions in one method when we solve a system. That's what we're looking for. So instead of writing the system like this in matrix form, we could write it in terms of x's and y's here. X prime y prime equals our matrix A times our vector xy. And see, when you multiply through on the right hand side, you get A times x plus B times y, and that's equal to x prime. You get C times x plus D times y, and that's equal to y prime. So we could also write the system like this. So for example, if you have a system of two first order equations written out like this, you can write them in terms of a matrix, and vice versa. So all we have to do is read the coefficients off of your x, y, 4, -6, 3, -7. X prime, y prime is the vector x prime, and this xy vector is your solution x. Now let's recall, we've discussed this previously. So if you're trying to solve a system of first order equations, we assume that our solution looks like v e to the lambda t, where lambda is an eigenvalue of the matrix A, v is an eigenvector of A, and we've learned how to find those. Now we're only going to be worried with 2 by 2 matrices. So when we do this, our characteristic equation will be a quadratic equation. And of course, quadratic equations can have 3 different types of solutions. You could have 2 distinct real roots, complex conjugate roots, or repeated real root. And we're going to skip the repeated real root case. So let's consider this problem. And this is a problem that will have 2 distinct real eigenvalues. So we're going to think about solving the system x prime equals this matrix A times x. Now in a previous example, a few times back, we found the eigenvalues and eigenvectors for this matrix A. The eigenvalues were -5 and 2, and these were their corresponding eigenvectors. And again, so we have 2 distinct real eigenvalues here. So this is the form of the solution. So for each lambda, we have a vector, so we'll have 2 solutions. So this is the easier of the cases. So we're solving this system where A is given. We have 2 solutions because we found the eigenvalues and corresponding eigenvectors. So the eigenvalue lambda sub 1 was -5. And the corresponding eigenvector was 2, 3. So the solution is v, the vector v, times e to the lambda sub 1t. Well, you can multiply this through and get this solution. So this represents the x component and this the y component. We do the same thing for the second eigenvalue. The eigenvalue was 2. The corresponding eigenvector was 3, 1. So we get the vector v times e to the 2t. And again, you can multiply this through. So this is the first solution, the x. This is the little y. Now it turns out that these are 2 linearly independent solutions. Now how do I know they're linearly independent? Well, one way to think about it in terms of vectors is that this vector is not a constant multiple of this vector. Another way to do it is to take the Wronskian. Now this is the Wronskian of 2 vector functions. It's a little different than when we did Wronskians earlier. If you do the Wronskian of two vector functions, you just do the determinant. You write the first function here, this one, and the second function here, this one. And then you just calculate the determinant. So here you'd have 2 times 1, that gives you 2, e to the minus 5t times e to the 2t, adding exponents, gives you minus 3t, minus 9, e to the minus 3t. When you subtract, you get negative 7 e to the minus 3t. That is not identically 0, and that tells you that the two functions are linearly independent. Now to write out your general solution, you just take a constant times the first function plus a constant times the second. That's what we're doing here. If you multiply it out, this constant times this plus this constant times this gives you this first component. That's your little x of t. Doing the same thing on the second row. 3c sub 1 e to the minus 5t plus c sub 2 e to the 2t. That gives you your second component. So that's the little y of t. You could further rewrite it in terms of a matrix times a vector of constants by just taking everything that has the exponential part, the 2e to the minus 5t, the 3e to the 2t, place those there. Do the same thing here, 3e to the minus 5t, e to the 2t, and then just multiply that by a column of constants. This matrix here is called the fundamental matrix, and this C is just a column of constants. And so another way to write your solution, X is the fundamental matrix times this column of constants.